All right. Got some more grading done, including half of last week's quiz already. So I'll have some more good random questions. Somebody asked about the different crystals of different types of ice and what that looks like. There's a couple of good examples, but let's see. If I get images, all right, so when we're looking at different types of ice, we're not going to be able to get a whole bunch of time into crystal structures in this class, but it turns out crystal structures are really interesting because they're a repeating structure. What makes something crystalline versus just having it be solid is that it's got a repetitive structure that repeats almost infinitely in 3 dimensions. Like for when you think about how many atoms are in a mole, like we can basically treat these crystal structures like they repeat infinitely. If you put water under different conditions, different temperatures, different pressure levels, you basically get each one of these blue boxes is what's called the unit cell, which is the part that's repeating. And you'll see that the unit cell actually looks a little bit different for all these different ice types. And so the distance between the water molecules can be slightly different. The angles can be slightly different. The way that they're arranged within the unit cell can be a little bit different. So they all still look like a whole bunch of water molecules arranged so that the polar ends of the molecule are pointed at each other. But what's a little bit different is going to be the actual angles and how much empty space there is in this unit cell. And when you take real Gen Chem as opposed to Intro to Gen Chem, we do spend a chapter, a week or two on crystal structures. And it's really interesting because anything material science based is going to come back to crystal structures a lot of the time. So understanding how they work, how they repeat, and how you can do things like derive the density of a substance based on the size of the unit cell and how many atoms are in it, for instance. Then the other random question that we won't be able to touch on too much in this class, but when we start talking about intermolecular forces, we'll be able to discuss it a little bit more. Basically, why are, and that's not just some species, everything that lives has a certain pH range where it can live. And even within that, it's sort of a bell curve. There's an optimum pH, and then things behave okay for a little bit of range on either side of that, and then it sort of drops off. And that's usually because what happens when you're too far away from an optimum pH is you either have too much H+ floating around or too much hydroxide floating around. And that's going to change the way that that proteins interact with each other and with themselves. So basically what happens when it's the same thing that happens when you get too hot. When you cook something, you denature proteins. The reason why we have to cook meat to avoid foodborne pathogens is basically you kill everything in it by taking the proteins and making it so that they misfold. And once the proteins are no longer folded properly, they don't work as enzymes. They don't catalyze reactions anymore. And the same thing happens to our enzymes as well. And that's also why you can cook, quote unquote, with acids. If anybody's ever had ceviche is technically cooked fish, but it's never been exposed to heat. You cook it by exposing it to lemon juice or vinegar, and that denatures all the proteins that might be in there that might be pathogens without exposing it to heat at any point. So it's basically getting outside that Goldilocks zone of what pHs are acceptable things basically start falling apart. And we even have like a range of pHs that are acceptable within our own body. We have enzymes that are evolved to work really well at the pH of our stomach, which is really, really acidic, right? If you take, they're called proteases. What they do is they break down proteins into smaller chunks. If you take those proteases that are developed to work at stomach acid pH, they won't work in DI water. Basically, they unfold. They're very specifically will only work at the pH range of your stomach. But if you take a different protease that's designed to work in your large intestines, for instance, or inside cells that keep foreign proteins from acting up, those ones won't work at stomach acid pH, but they'll work in the pH of your cells. Did I see a hand a second ago, Diego? Yeah, so one of the things it does is it breaks down the cell membranes and dissolves your skin cells, but it'll also denature the proteins as well and cause much the same reaction as burn, a heat burn. If you take biochem, we get to spend a whole class talking about protein structure and the nature of protein bonds and how they all fold up properly. All right, these are a little bit more relevant. I usually mention this. Somebody asked about absolute zero. How close can we get to absolute zero? And I told you that the substance, the element that boils at the lowest possible temperature is hydrogen, and it boils at about 2 Kelvin. We can get colder than that, though, which seems like, how do you get some colder than the coldest boiling point out there? Turns out you can use something called laser cooling, which is when you shine a laser on something, but instead of heating it up, turns out if you shift the frequency of the laser down just a little bit, you can actually get things to slow down. So if you think of a laser heating something up, or light as heating something up, just like pushing someone on a swing, you have to time your pushes, right? If you time your pushes properly, the amplitude of their swing gets bigger and bigger. That would be like heating something up. The amplitude of the atomic motion gets bigger and bigger. If you time your pushes on a swing correctly, though, you can actually slow someone down, right? If you're absorbing the energy with your arms instead of pushing energy in. It turns out if you shift the wavelength of the laser just below the frequency where that material normally absorbs it, it'll actually cool something down. So we can get actually really, really close to absolute zero. We can get to a couple hundredths of a degree Kelvin, a couple hundredths of a Kelvin. But the thing is, we can never really get to absolute zero. And it's due to the observer factor. The same principle that we saw with when we were talking about electrons, and electrons are either here or there. So we treat them like they're a probability function. But when you measure where they are, that changes their position, right? The act of measuring. If you think about absolute zero as being the point where all molecular motion stops, how do you measure that without putting something else into contact with it and messing up that perfect absolute zero? So you can never actually, even if you could get to absolute zero, you couldn't measure something as being at absolute zero, because just by measuring it, you're going to warm it up. So, think about if you take a room temperature thermometer and you put it in your mouth, thermometer warms up, but for a second, your mouth cools down, right? So try to think about measuring the temperature of something that cold with something room temperature, even something else that's really, really cold. Just if our definition of absolute zero is all motion stops, by bumping into it to measure it, you disrupt that.
It would take that couldn't reach, like make something that's measuring tool that would reach absolute zero, and then it would measure itself.
You still have to communicate somehow, and then even then you would have to put it into a perfect vacuum where there was nothing else around it. We know perfect vacuums don't exist, right? Even in deep space. So basically, as soon as you got something to absolute zero, even if you could measure it at absolute zero without disrupting it, something's going to bump into it. You wouldn't be able to keep it. You wouldn't even be able to keep it long enough for it to register in all likelihood. But basically, like, it's not technically impossible, it's practically impossible. Does that make sense? You know?
It's not measuring it like literally like on a thermometer. We measure it by understanding what happens to something once it's at absolute zero. So like if we knew what would happen.
Potentially, that's one of the ways that we measure what happens with black holes.
Okay.
Is we can't measure what's happening inside the black hole, but Stephen Hawking was the one who put forth the idea that we should be able to see this weird form of radiation from the surface of a black hole. Even if we can't see the black hole itself by its definition, there's these other phenomena around a black hole that we could measure. So there might be something like that, some way we could use logic and our knowledge of the universe to kind of work around measuring it directly. But you still have the same problem that as soon as you make it, it's gone. By its very nature and just how matter works and bumps into itself, other matter. Somebody asked about if we replace copper 2 chloride with another transition metal compound in the same reaction, how would the yield of iodine be affected? Now it ties into that question after that. How do scientists first discover equilibrium? Because basically, if you look at the different yields that you get, the different yields that you get are based on equilibrium for the most part, right? And it turns out our equilibrium constant, you remember this, I've written this equation a few times on the board. Basically, equilibrium constant for a reaction is based on the change in energy for the reaction divided by R, which is our gas constant, but in energy units, divided by temperature in Kelvin. What this really means, though, is if we have a reaction where there's two possible states, there's your reactant state and your product state, the equilibrium constant is going to be based on what's the difference between these two. Delta G is another very specific form of energy, so we can just think of it as energy. The distance in energy between products and reactants dictates what K is. If delta G was 0, K would be 1, meaning that at equilibrium, you would have equal amounts of products and reactants. As you change what the reactants are, like the question up there, you're going to change what this distance is between products and reactants, which is going to affect your equilibrium constant. So there are other metals we could have replaced was in relation to that reaction that had you write with copper chloride reacting to make iodine. You can do that with a different transition metal and it would work just fine, but you're not going to get the exact same equilibrium constant because copper and copper 2 chloride have their own values of energy that fit in here. If we used something else, this delta G number might be smaller or it might be bigger. Depending on what this difference in energy is, that's going to affect what your equilibrium constant is. So we could get some yield, but it's never going to be the exact same yield because you're not going to have the same equilibrium constant. And as to how they first figured this equilibrium out, basically they realized that you could get to equilibrium from either direction. It doesn't matter if you start with products or you start with reactants, you end at the same ratio, regardless of where you start. So really it was experimental at first. They realized that if a reaction can happen backward, but you get to the same ratio of products over reactants no matter what, then that's actually where the whole concept of equilibrium came from, was realizing that, was measuring that difference in, or getting the same ratio regardless of where you started. And then why do some reactions react quickly while others react more slowly? Turns out it's related to this. What determines how fast a reaction happens is the activation energy, which is basically what's the barrier between reactants and products. This energy between where you start and the highest point, you can think of that as like going through the pass between here and Carson City. Lake level, Carson City are your overall reaction energy. Getting through the pass determines how much gas you have to spend to get there. And it turns out it actually has a very similar relationship there. We use a lowercase k equals a constant times E to the activation energy over RT. So basically, it's the same form of the equation. And what that means is that the higher your activation energy, the slower the reaction is going to go. So the reason that some reactions happen slower than others, something might have a really, really high equilibrium constant, like say combustion of wax. We talk about burning a candle. If you burn wax, that favors the products 10 billion to 1. However, if you just have a wax candle sitting at room temperature, it doesn't go up in flames on its own, right? Because the activation energy of wax burning is high enough that none of those molecules are moving fast enough at room temperature. None of the molecules are moving fast enough to make it over the barrier and start that process. Right, so it's really two different things. The equilibrium constant is what's called thermodynamics, and that's just all about predicting yields and how once you get to equilibrium, what are those ratios going to be? How fast you get there is called kinetics. And that starts getting really more interesting mathematically too, because we have to start bringing calculus into it. Because when we're talking about rates, we're talking about changes in things, which means we're talking about derivatives and slopes. You don't actually have to take the derivatives in Gen Chem to get there, though. If you take Gen Chem without having taken calculus, it's just the concept of a slope shows up. All right. Let's do practice with combined gas law. So a balloon is initially filled up to 1.05 atmospheres at 22.0 Celsius and a volume of 5 liters. When the balloon warms up, the temperature increases and the volume increases. What's the pressure inside the balloon? So if we're going to use the combined gas law, what does the combined gas law mean? What is it? There's the ideal gas law, but then there was P1, V1, N1, T1 equals R, but we're not going to use that in this case, equals the after conditions, P2, V2 over N2, T2. Now, are all of these variables changing? What's remaining constant? A balloon is filled up. Once you fill the balloon up, the moles of gas aren't changing within sig figs. Obviously, we've all seen a balloon eventually lose its inflation, right? We'll talk about that process later. But basically, within sig figs, we can say the moles of gas is the same. And if it's the same on both sides of this equation, what can we do? If N is the same before and after, we just can't cross it off. It's going to cancel out. So we have 3 variables before, 3 variables afterwards. Like I've said before, though, I have to give you a whole bunch of information to be able to do this, right? So it's all about recognizing what goes where and getting the right units. So P1, 1.05 atmospheres. T1, 22.0 degrees Celsius. We can't leave it in Celsius though, can we? Nope. Put it in Kelvin. 295.2. V1, 5.00 liters. P2 is what we're solving for. V2 is 5.05 liters. P2 is 40.5, which is 213, or sorry, 313.7. So we're given all this information. Now we just plug it in and solve for the one we're missing. So a little bit of arithmetic, little simple algebra, nothing tricky here. You need a calculator, don't you? What do we get for a number? One what? 0.143? That doesn't make a whole lot of sense. 1.91 makes a little bit more sense. That seems a little bit high, though. That's about what I was expecting. So does it matter that all these things are changing at the same time? As long as we can measure enough of them, we just have to be able to solve this. If it's not something where we have 5 out of the 6 variables, we might not be able to solve this, right? You have to have 5 out of the 6 variables to solve this, or you have to start thinking about a system of equations. But that starts getting into be a much more complicated question than this, right? The simple case is that you're just given all the information you need. All right, we said that n was a constant. We weren't given n. Could we figure out n? Yeah. The other form of this reaction was, or just, we usually just write it like this. As long as we have 3 and we know that r is always the same, we can get n. So 1.05 ATM, 5.00 liters equals moles times 0.08206. Which again, you don't have to have memorized because it's on your conversion sheet. Double check your units though, liters, atmospheres, moles times Kelvin. That all matches up, right? If I did something mean like give you your pressure in PSI, then you just have to do a conversion on your pressure to figure out what it is in atmospheres. So when we solve for n, see it, these conditions, something around 0.25. We check all of our units. The only thing that doesn't cancel out is moles. Quick note about PSI and pressure conversions in general. Other than 760 torr equals 1 atmosphere, all of the other pressure units are measured. So 14.7 PSI equals 1 atmosphere. That's only 3 sig figs. 760 torr is defined as exactly 1 atmosphere, so that one's exact. But, and 101.325 pascals, 1 atmosphere, I believe that one's measured as well, but how often do we need more than 6 sig figs? So the one that you really need to pay attention to, the one that showed up on the quiz this weekend, if you were off by sig figs, it's probably because you treated that 14.7 like it was exact. Don't worry, it's only a quarter point off. All right, so gas laws questions so far.
What would be the order of operations to put that in the calculator to get it?
Shouldn't matter because multiplication and division are really the same step, right? So since there's no addition and subtraction, there's no exponents involved, you should be able to do it in any order. 1.05 times 5 divided by 0.08206 divided by 295.2 should give you the same answer regardless of what order you do those steps in.
I was trying to multiply the art screen by
So if you multiply these together first, you can do that, then you're gonna, but if you divide it by this number, then you just had it backwards.
Yeah.
But yeah, you can simplify these in order to do it in whichever order you want, as long as you make sure you're multiplying and dividing where you're supposed to. All right. One last concept when it comes to PV equals nRT before we move on to some other gas law stuff. One of the things that's really helpful about PV equals nRT is that we can rearrange these variables to solve for other things. For instance, we can actually solve for moles per liter. If we solve, which is basically a concentration unit, right? If we rearrange this, we can solve for N over V, which is our definition of molarity, right? N over V is equal to pressure over RT, which, okay, I just did some algebra. How useful is that? Well, we already have some experience though using densities and molarities as conversions, right? So if we pick a standard temperature and pressure, we just are going to call like the general common conditions worldwide. We can actually figure out what this ratio is at that pressure and temperature, at standard temperature and pressure. And we can actually get a number for it that it's going to allow us to convert in one step, to convert between volume and moles, as long as we're at standard temperature and pressure, STP. So standard pressure. Makes sense to call standard pressure 1 atmosphere, right? That's kind of our definition of 1 atmosphere, is that it's the normal pressure. Why would they pick 0 Celsius to be the standard temperature? Where water melts. That doesn't really apply to gases though, does it? Well, it used to be somewhat of a fixed number. One, it makes the conversion to Kelvin really easy too, right? 273.15 Kelvin. The other thing that's really helpful, or used to be really useful with 0 Celsius, is it was a pretty good number for the average temperature of the atmosphere. If you average the temperature of the atmosphere over the entire planet, over the entire year, it comes out to be really close to 0 Celsius, it turns out. So up until climate change became as measurable as it is today, this was actually a pretty good estimate. If you had to pick a random temperature and say, that's my normal temperature for a gas, 0 Celsius was actually a pretty decent number to use. Plus, it makes the conversion to Kelvin that much easier too. So we use 1 atmosphere and 0 Celsius for standard temperature and pressure. And if we plug those in here, we're going to get a number for moles per liter. Right, so plug in 1 atmosphere, let's call it exactly 1 atmosphere. 0.08206 liters times atmospheres, mole Kelvin. And 273.15. Kelvin cancels Kelvin, atmospheres cancels atmospheres. So at these conditions, we're going to get a ratio between moles to liters. It's going to be 0.04. So 1 over 0.08. That answer divided by 273.15. Give me 4 sig figs on it. That's going to be moles per liter. This unit is now a combined unit, right? Which actually means we can do a conversion where we convert straight from liters to moles just in one step, the way we've been using conversions like density and concentration. So at standard temperature and pressure, the molarity of a gas is 0.04461. That's kind of useful, except we don't usually like numbers that are less than 1. So a lot of times you see this number flipped in terms in liters per mole instead of moles per liter. If you put this number in liters per mole, all we have to do is do 1 over this number, right? It allows us to say 1 mole of gas at standard temperature and pressure is 22.414 liters. 415. It's a rounding error in there somewhere because this is one of those numbers I've drilled in my head. So if you, it's actually on your conversion sheet as well. The trick is this only works at STP. If we're not at standard temperature and pressure, we actually just have to use PV equals nRT. We have to break up our conversion. But this is just sort of a shortcut, and it's a good way to do a reasonableness check. On the slide before, when we were looking at how many moles was in there, it said, oh, it's 1.05 atmospheres at room temperature, and it's 5 liters. I didn't have to do that math in my head to get a reasonable number for it, because I know 5 liters is about a quarter of 22. And I know that 1.05 atmospheres is pretty close to 1 atmosphere, and room temperature is pretty close to 0 Celsius in terms of Kelvin. So it gives you a decent way to estimate in your head how many moles of gas do you have, even without having to plug in the numbers and get the real answers. anytime we learn a new way to solve for moles, to figure out how many moles are in a system, what's the first type of problem we try to apply that to? Give you a hint, it was roughly 30% of the midterm. Stoichiometry. We can do theoretical yield with gases now. Everybody's favorite thing to do. Because every time we find a new way to get to moles, we figure out how we can apply it to a reaction. This is the easiest way to do that. It's not so bad though. Only thing that's going to change, it's a theoretical yield question, except at the end, instead of figuring out how many grams of product you're going to make, you're going to use this conversion to figure out how many liters of product you can make. So it's really, it's more of the same. What reaction is this? Not combustion. It's a weird looking acid base reaction. Look at what the reactants are. What's acetic acid? Vinegar. What's sodium bicarbonate? Baking soda. This is vinegar and baking soda. If you want to know how many liters of foam you're going to make doing your volcano middle school project, here's how you get it right. So it's not just guess and check. You better believe if my son asks to do a volcano project for his science project, we're going to be doing this before we actually start mixing stuff, because this is more fun. More fun to do math than just guess, right? Maybe. It is kind of fun to see what happens. It's less messy to do the math first. We'll put it that way. Maybe not more fun. How many liters are you asked we're going to make? So excess vinegar, 10 grams of baking soda. Well, we need molecular weight, right? So 23, 24, and 12 is 36 plus another. What do we get? 3 times 16. I should be able to do that in my head. 48. 48 and 36. What do we get for a molecular weight here? I know it's review, but I want to stay current on these things. Anybody? Am I going to calculate it first? (23 plus 1.008).
10 grams of
So just give me the molecular weight of sodium bicarb. There it is. So we'll start with that. Then, because it's already balanced reaction, you can say 1 mole of sodium bicarb makes 1 mole of CO2. And what's the last step? Once we get to moles of CO2, if we want liters at STP, right there, for every 1 mole of CO2 makes 22.414 liters of gas. So something like 3 liters, 2.5 liters. Ish. Do we need to be able to do this if we're just talking about the baking soda volcano? We don't really need to do this calculation because it's what is the downside to underestimating how much foam you're gonna make.
Couple.
Yeah, you have foam on the kitchen floor. However, if this was more dangerous chemicals, then we kind of want to know if we're going to be making 10 times more than we expected, right? 2.67 liters is not that big, but it's not small. You know, that's about a liter right there. So 2.5 of these, enough that it could make a mess, not enough to be dangerous, right? Anybody seen the Mark Rober video where he does the elephant toothpaste? He does the calculations ahead of time to figure out how much of everything he needs. Well, it depends on which one you're watching. It also had the problem of the temperatures changing. So it was actually a more interesting math problem than this because it wasn't remaining at STP at any point. So they needed to figure out how to get it mixed at the right temperature without denaturing. He didn't use catalase, I don't think, in that one. He used a metal catalyst. So those don't denature. But if you're using the classic example with yeast as your catalyst, then you have to worry about the fact that once the temperature gets too hot, you're going to denature that enzyme, like we talked about at the beginning of class. So it was more complex than that. Turns out scale up is actually is the single biggest obstacle in chemical engineering. Is not how do I do it, it's how do I do it at a huge scale for as cheaply as possible. That's 95% of the questions that you have to answer as a chemical engineer is how do I do it bigger and cheaper? And it turns out you don't really get very good at that until you get to your 40s. If you look at process engineers, which is a specific type of chemical engineer that design factories and refineries, they start making a whole bunch of money once they get into their 40s. And that's when they're expected to be the most productive because you've got 20 years of working in factories and working under other process engineers to pick up all the tricks. Don't get me wrong, you're still paid well for that part too. But you start getting really well paid once you hit your 40s. Which is why I'm going to go to all my chemical engineer friends that work for Chevron when they hit their 40s and start getting paid and have them start bringing me on vacations. Exactly. And if you just want a paycheck, it's changing a little bit given the nature of how global energy and petroleum is changing. For a long time, chemical engineering was basically petroleum engineering. Now there's a little bit more to it than that, but the best paying jobs right out of undergrad are still working for the petroleum companies, doing different things sometimes now. But my buddy who got a job for working for Chevron right out of undergrad got hired at $65,000 a year at 22. And this was now 15 years ago or so. So that was a lot more. It was a lot of money. It's still a lot of money. It really was a lot of money then. So anyway, if you don't mind working for a place like Chevron and you value money, chemical engineering is a great field to go into. So has anybody heard of the Hindenburg?
Oh, yeah.
Worth note, I got told off last quarter because I didn't bring this up. This is also notably the cover of Led Zeppelin 1. Uses the same image process a little bit. Because does anybody know how Led Zeppelin got their name? I can't remember who it was. I want to say it was Eric Clapton. Because it's about the right level of foresight for that dude. But somebody said that Led Zeppelin sound was going to go over like a Led Zeppelin. Basically, they're going to sink, crash and burn. Obviously, that's not how it worked out, but they thought it was funny enough they took their name from it.
It was Keith Moon.
Keith Moon. There it is. Thank you. Well, can't say he had a whole lot of foresight as he died not too much longer after that. If we wanted to figure out how many moles of hydrogen were in there, we can assume STP. If we know cubic feet of hydrogen gas, we can get to liters of hydrogen gas, right? If we can get to liters of hydrogen gas, we can get to moles of hydrogen gas pretty quickly if we assume STP. How do we get from cubic feet to liters? Go to cubic inches, cubic centimeters. Yeah, so we could go 1 foot is 12 inches cubed. 1 inch, 2.54 centimeters cubed. And then we can say 1,000 centimeters cubed is 1 liter. Then we can go to moles. Nothing we haven't seen before other than this last step, right? What if it's not at STP? We can still get to the volume in liters, right? If we're not at STP, we need to know what the pressure and the temperature are. But then if we're not at STP, we just stop here and then we plug it into PV equals nRT. We need more information, but you just like anything else with these gases, you need to know enough of the variables. You get a really big number when you do this. And incidentally, this is why we don't use hydrogen in airships anymore.
Trial and error.
Can anybody, this is more of a music history question. Any other famous bands that took their name from reviews that disparaged them? No, they took theirs from a movie theater that was playing a B horror movie starring Boris Karloff across the street from where they were practicing. I was thinking of Daft Punk. Their first EP before they went by the name Daft Punk got a write-up in the London Guardian or something like that, where they said they referred to it as Daft Punky Nonsense. And they thought, hey, that's a pretty good name for a band. And look how that turned out. All right. We're gonna skip this because I think we've been doing a good job reviewing this. Basically, when we talked about stoichiometry now, we just have one more way to get to moles of stuff. We had molecular weight to go from a mass to moles. If it's a solution, we use a concentration to go from volume to moles. If it's a gas, we're going to use the ideal gas law to go from volume, pressure, and temperature to moles. Right, but it's just one more tool in our toolbox when it comes to talking about these chemical reactions and predicting things like theoretical yield, excess reagent, etc. All right, I know it was the very last thing we went over on Friday. It's going to be very close to the last thing we go over again today. But before you get up, who remembers what the assumptions in the ideal gas law were? What were we assuming for the ideal gas law to work? We were assuming no intermolecular forces, which also means what?
No phase change.
No phase change. Basically, in order for this to work, we have to assume that the volume versus temperature is actually proportional. If you drop the temperature enough, the volume goes to 0. That's not actually how things work, right? You actually have a gas and you drop it down close to 0 Kelvin, it goes through a phase change. And even if you could get it to 0 Kelvin, the volume is not going to be 0. Why is that? What's the other assumption?
Gas molecules at 0 volume.
We're assuming we could get to 0 volume at 0 temperature, which means we're assuming the gas molecules have 0 volume. Right? If either of those assumptions is not a good assumption, If you have strong intermolecular forces, like water does not behave as an ideal gas very well. It has really strong intermolecular forces. It goes through phase changes at relatively high temperatures. So water is not a great candidate for the ideal gas law. But it's usually good enough, as long as you're not close to a phase change, and as long as you have a lot more empty space than molecules. So your ideal gas law is going to break down at high pressures, high concentrations of molecules, and if you have molecules that stick together, that are really polar, then those assumptions break down. And I just wanted to say that one more time, because I will just about guarantee that one of the questions on the final exam is going to ask you what those two assumptions are. So you don't have to memorize what, I guess you kind of have to memorize what they are, but I would like it if you could explain why those two assumptions are the way they are, but at the very least know that they're there and where they break down. Okay. All right. We're done for today. So like, I think the way the question works, what assumptions we have to make for the ideal gas law. It's basically, we have to assume that the molecules don't interact. We have to assume that they don't think of any volume or a significant chunk of volume.